So far, any question, anyone? Any question? Can I have a raise of hands if you all are following, please? Hafiz, Sharif, Nabihan, Asfar, Murtaza, Muhayman, Arif, Nur Shakira, Ikenyo, Yuvan. All right. So let's proceed with the next agenda. So far, we have seen um, the low pass filter and the high pass filter. Thank you very much, everyone. Thank you. Now we'll move further. So far, we have seen either RC or RL, and we will be looking at circuits having all R, L, and C components. Okay, and then we have to see what are the effects of that. But the most important thing that we want is to have resonance. Resonance is basically, okay, let me read it for, is a condition in RLC circuit in which the capacitive and inductive reactance are equal in magnitude, thereby resulting in purely resistive impedance. First, let me ask you, have you guys seen such condition anywhere before? There's an RLC circuit and we the end result is that it's purely resistive. Can anyone recall from circuit theory? There was one condition in which we said that the impedance is purely resistive. Can anyone recall? Okay, let me give you a hint. When we have a inductor or capacitor, if you remember, we will have either a voltage or current lead lag issue. So we'll have like two of the values having some angle between them, and the resultant of the V and I will be a bit, the product is like a bit not full, I would say, right? But if they're all like one on top of each other, then it's like zero phase difference, which is the resistive case. We get an advantage. If anyone can recall from this description, if I'm not confusing you even more. All right. If you remember the condition of maximum power transfer theorem, in which the impedance, the load impedance, let me draw it here. This is the system impedance. And this is the load impedance. This is impedance. The maximum power was transferred when, can anyone recall again? Maximum power was transferred when ZL was Z's complex conjugate if you have covered this in circuit theory. And of course, this means that if suppose Z is R plus JX, and if we talk about ZL is the conjugate of Z will be R minus JX, and the series combination will be the Z equal will be R plus JX plus R minus JX. So this will go, it will be 2R. The important thing is pure resistive, no reactive element. Okay, and in that case, the voltage and current phase difference is 0. So they are like this, and you know that when cosine product of two in phase vectors is the maximum. So we'll get VI, which is power, as maximum. Okay, just a recap from circuit theory. Have you guys seen this before? Have you guys seen this condition before? Yes or no? Anyone? This condition or maximum power transfer? Okay, thank you. So this is just to get a recap. What we want to see is the resonance. Okay, now maybe you already got the hint that in case of resonance, the sort of the circuit is performing the best, I would say. Okay, we want to have this in a circuit, and this is happening when there are components of different frequencies oscillating together, but the maximum impact is created when all of them are in phase or in constructive what's called in light. I don't remember right now, but they are all in phase. In phase means there's no phase difference, so they all, if you, oh, that's in control systems. But if you will read through in control systems, when the soldiers, the army is marching, when they reach a bridge, they are asked to break their steps. Do not have the same marching sequence, because that may cause the bridge to resonate, and just by marching the bridge may collapse. All right, so this is something, but for some applications we want the resonance to happen, and that makes the system perform the best. All right, so we want to have this as purely resistive. Okay, this means the J has to go. In this case, if you look at it, if suppose Vs is the source and the current is the just impedance, actually this is just impedance. All right, so what we want is this thing to go. This, if you remember this j omega L, and 1 upon j, so 1 upon j is negative j, so negative is here. So what we want is this thing to be 0. Okay, so resonant results when the imaginary part of the transfer function is 0, or imaginary part of z omega L minus 1 upon omega c is 0. Are you guys following so far? So if we want our circuit to perform at resonance, these two have to cancel out each other. Okay, so the inductive reactance and the capacitive reactance, they have to like cancel out each other. If you remember the voltage lead and lag, the capacitor voltage leads and in inductor current the opposite actually. Capacitor current leads and inductor the opposite. But if they all work together, they will be like cancelling out each other. So this has to be 0. And the condition is, so the omega naught, as we said before as well, omega naught is the resonant frequency, and this is coming from this equation. And we can find omega naught just simplifying it, omega naught square and omega naught equal 1 upon under root LC. This is the resonance frequency for a series resonance, series circuit, series RLC circuit. This is the resonant frequency. And since remember it's 2 pi f is, so we just there's a 2 pi f is the omega in terms of hertz. So far so good. Any question? This once again, these are basic concepts. We will be eventually using some formulas to find these things, but this is basic understanding. All right. So the features of series resonance is impedance, as we just found out, is purely resistive. There is, so if we try to find out the impedance of this, it is purely resistive, as we have seen that these will be cancelling out each other. All right. Supply voltage Vs and the current I are in phase because of no reactive component, no phase difference between voltage and current. So the power factor is 1. Have you studied power factor before? Power factor is determined by the phase difference, and it's determined by cosine of that angle. So remember that power factor is cos phi, where phi is the angle between the voltage and the current. So if this is 0, cos 0, which is 1, so this is what makes the power also to be maximum. And just to let you know, the power that comes to our home, we want that to be as high as possible in terms of power factor. If it is lower than 1, there are losses, inductive losses. And since most of our appliances at home are inductive, like motors or lights, or most of them are inductive, that's why you must have seen some capacitor banks or capacitive device to be attached in your house that reduces the that increases the power factor. You can find on the internet, if you want to reduce your bill, you can use a capacitive load. Just plug it in, and you can maybe 5-10% of less electricity bill can be expected. Anyways, so for series resonance, the power factor is 1. Magnitude of the transfer function Hz is z. So this is minimum. Magnitude is minimum. That's why we expect a maximum power transfer as well. Inductor voltage, capacitor voltage can be much more than the source voltage. So it's not right now. It's not because these are either open circuit or short circuit or something. So we don't expect that it is following this voltage. It may be much higher. All right, so the frequency response of the resonance circuit. So once again, we will go for the transfer function thing. In this case, yes. So the current I, or the magnitude, is like if you apply mesh for the voltage, the total impedance Vm. Actually, this is like sort of I upon Vm. So don't worry, this is like transfer function. That's why we are calling it the. Okay, since the omega L and 1 upon omega C will be cancelling out, so the power will be average power will be half I square R, and the highest power will be happening when Vm is maximum. Remember, this is a sinusoidal voltage, so at maximum values will be the maximum power dissipation, and it will be occurring at I equal Vm upon R. Vm is the maximum value, and if we want to like plot it, the I will be like this. Don't worry about this B and omega naught and omega 1, but omega naught is the resonant frequency. This is the most important thing right now. And this happens when Vm upon R. All right, we'll come to the other terms in a while, but these are some formulas to remember to find the average power. This is the average power is half I square R. Highest power dissipated is half Vm square upon R. This is happening when we just put this here. Arif is so excited, huh? Okay. Okay. So now what are those particular frequencies that I just mentioned, omega naught and omega 1 and all? So you can see that at omega naught, it is the maximum power. Okay. But uh, we would like, of course, to have this power to be at the optimal level, and but this is not always possible. So just like in the previous low pass filter and high pass filter, we set a threshold that okay, this is the level that if it is like above this, we will consider this as pass and stop. So we keep the same 0.707 value. Okay, and eventually I would like to just keep it a bit short here. This is coming from 0.707. I'm not showing the derivation, but eventually at p omega 1, at omega 1, the power will be Vm squared upon 4R. Okay, this is because 0.707 is 1 upon under root 2. So we are putting Vm upon under root 2 in the formula, and we get Vm squared upon 4R as the power. And the good thing about this is that this is half of the actual power. If you go back, the maximum power was 1 upon 2. This is important. 1 upon 2 Vm square upon R. 1 upon 2. I should have written that in the next slide. The power was P max was 1 upon 2 Vm square upon R. But at omega 1 or omega 2, at which is like 0.707, it is half of that. Half of that. So it's like 1 upon 4. It's like divided by 2 will be 1 upon 4. All right. And if we want to find the frequencies, we can set the Z magnitude as under root 2 upon R. Again, I'm not showing the derivation here, but I'm setting the Z magnitude. The Z is here R square plus, this is the real square plus imaginary square coming from the original circuit. I'm setting it equal to under root 2R. The magnitude, this is actually Z magnitude equal this. I'm setting it to under root 2R. And the at what frequency it will occur. If you want to find the frequency, so if you go back, let me just remove all the ink from here. If this is my circuit and I want to find out the omega naught and the frequency at which we will still be having half the power. So that's what we call omega 1 and omega 2. Omega naught is the resonant frequency, and the omega 1 and omega 2 are the frequencies at which we are still having half the power. So yeah, once again, this is the resonant frequency, and omega 1 and omega 0 are the frequencies at which we are still having half of the maximum power. This is the maximum power, so just half will, they will be occurring at omega 1 and omega 2, and we are trying to find at what frequencies that they will happen. So it's like, so we use this expression and we just separate out omega from here. We get, because of the quadratic thing, we'll get two values, omega 1 and omega 2. So one of them, they're actually the same except there is a negative sign here and no negative sign here. So all the same except these is, there's a negative sign here. All right, I don't think we need all this much of ink here except maybe Z. right? And if we want to relate the half power frequencies with the resonant frequency, it's basically omega naught equal square root of omega 1 omega 2. Okay. All right. Do you guys know what is bandwidth? What is bandwidth, guys? What is simply bandwidth? Anyone, any idea what's a bandwidth? What's band? All right. Let me just start with very simple thing. The rainbow, the rainbow is a band of colors having different frequencies. Violet, indigo, blue, green, yellow, orange, red. This is like a band. It's like a hairband or a rubber band. It's a band having different frequencies. So whenever we say band, it means it's a set of frequencies. Just like in this particular thing is also having some frequency. And when we talk about bandwidth, we see what is the range of that. So in this case, it will be like omega 2 minus omega 1. And which is what we'll see next is the bandwidth is, in this case, omega 2 minus omega 1. So the bandwidth, when we talk about band, is like, if you are listening to the radio, the FM band is between, I believe, 88 until 108. Medium wave is from 540 to 1000 something, and short wave and all those. And then there's this 5G. So they are talking about a particular bandwidth, okay, frequency bands. So so basically, in this case, we're talking about the half power bandwidth. So between this band, the power is at least half or more. So when we talk about the bandwidth in this particular topic, we're talking about the range of frequencies, the range of frequency between which the power is like from 1/2 starting to go to the maximum and then come back. So the minimum power it has is still half of the maximum power, right? Clear? So once again, some formulas to remember. Okay, quality factor. Quality factor is, is something like this. This is the same plot, but for different R and L values. So previous one looks like, I think this one maybe. So this can be modified based on the values of R, L, and C. If you can change this, we can change. All right. You can see that the bandwidth of B3 is the smallest, B2 and then B1. Okay. So if the application requires wider band of frequencies in which we want to have good enough power, we will have B1. But when we have this, we have a compromise on frequency. So have you ever tuned the radio? Have you ever tuned the radio for FM? You do it manually, so you just go to the exact frequency, and when you set your tuner to that frequency, the voice is the best. But if you go a bit left or right, like if it's suppose 100 FM, 100 megahertz, if you go 99.9 or 100.1, there's noise, so the quality decreases. If you go maybe 99.8 and 100.2, between this range, the voice further deteriorates. So the quality decreases. Okay, so if you tune it to the best frequency, the width, the range of the frequency will be like very small width, but the quality is the best. You can see that this one has the least selectivity. I'm selecting the frequency to the best. So for ideally, it should be like this. Ideally, the width should be 0 and the quality will be the best. Okay, so but this is this trade-off between quality and bandwidth. Quality factor is the ratio of the peak energy stored in a circuit and energy dissipated by the circuit in one period at resonance theoretically, and numerically they are equal to these numbers. And of course they are inversely related. They are all related like bandwidth and the quality and omega naught. So there should be another one related to CR as well. It should be CR. Omega naught squares here. Omega naught. We want to have to relate this one with. So Q will be omega naught square somewhere here. Omega naught square. This can be related. All right. The quality factor is the ratio of its resonant frequency to its bandwidth. Okay, so resonant frequency and bandwidth. If we just Q equal omega naught upon B from the same thing. If the bandwidth is narrow, the quality factor of the resonant circuit must be high. So if we are very sure, we are very focused on choosing the frequencies, we have a high quality circuit. If the bandwidth frequency is wide, the quality factor is low. Okay, I may have to speed up a bit. So yeah, one more thing. Said to be high Q circuit when its quality factor is equal to or greater than 10. If the Q factor sorry, is more than 10, it's a high quality circuit, and the plot will be symmetric. So it's not necessary always to be a symmetric plot. It could be skewed like this as well, or skewed like this as well. But for high Q circuit, for Q greater than or equal to 10, it's symmetric. This means that omega naught is in between omega 1 and omega 2. What are omega 1 and omega 2? Once again, omega naught is the resonant frequency, and omega 1 and omega 2 are the frequencies at which we still have half of the power left. Okay, so for high Q circuits, the half hour frequencies are symmetrical around the resonant frequency and can be approximated as almost approximated as like this. So if you know, if you remember that this distance is B, so omega 2 is omega naught plus B upon 2, and omega 1 is omega naught minus B upon 2 from both sides. Is that clear? Okay, so now we come to the part that you're going to ask, sir, is this going to come in the exam? So this will be coming in the exam. Okay, so you're given a circuit with some values. You have to find the resonant frequency, half power frequency, calculate quality factor and bandwidth, determine amplitude of current at omega naught, omega 1 and omega 2. So those who were just sleeping until now, you can wake up. This is the part that you must be interested in for the test and the exams. Okay. Okay. So the resonant frequency, if you remember, is 1 upon under root LC. Okay, so we have the value of L, we have the value of C. We can find omega naught very easily. I think now that we have all the formulas, it's now straightforward to, but it's important to understand all these things. So resonant frequency is 1 upon under root LC. We have L, we have C. We just put them in the value. 50 kiloradians per second is the resonant frequency. What should be the half power frequency? Yes or no? I'm asking yes or no. Should it be 25 kiloradian per second? Yes or no? Half power frequency. Yes or no? 5 seconds. Answer, please. No. Okay, very good. This is not. These are not. Okay, thank you, thank you, thank you, thank you very much. These frequencies are not half of the resonance frequency. These frequencies are the frequencies at which we will still have half of the power. So we have the formula for that. Omega 1 is minus r upon 2l plus under root r upon 2l squared plus 1 upon lc, and omega 2 is without the minus. So this is omega 1 and omega 2 is, so it's 49 kiloradian per second and 51 kiloradian per second. What do you say about these frequencies? Do we expect a high quality circuit or not? High quality because they're equidistant from omega naught, 50 kiloradian, 49 and 51. So this means they are high quality because they seem to be symmetric. Very good. So the bandwidth is 2 kiloradian per second, obvious. And this can also be found out by R upon L also. And the quality factor is 25. You can see 25 is much more than 10. So it's a high quality circuit. That's why we were able to identify this. All right, so these are the two methods that we can use to find Q and B. All right. Yep. We have done that. So same, we have seen that 49 kiloradian per second and 51 kiloradian per second. At omega equal omega naught, remember Vm upon R. So Vm is given 20 cosine something. So R is 2. So 20 upon. Why didn't we keep L and C? Because the effect of those have been cancelled. Remember this is the circuit. This is the circuit, but due to resonance, the effect of these are cancelled and we see only R. So for half hour frequencies, we just put under root 2 instead of R, and we get this, and we can get the power as well. This is the tutorial question. Oh, so we're still doing it now, actually. Okay, this is parallel resonance. The last one was series. This is parallel. Parallel RLC circuit is actually the dual of dual of series RLC circuit. So we can use duality. So previous one we use impedance. This one we can use admittance. So it's the same. I'm not going through all the steps here. The same thing. This has to be cancelled. The imaginary part must be 0, same as before. Resonance frequency we can find out, and looks like we still have the same frequency, right? I have a hyperlink here. I'm going to the series resonance. It should be going there. Go, go, go. Why not? Pointer. I was supposed to go there. It is betraying me. If I was clicking here, should I click somehow? Ah, yes. So I'm going to the series resonance. Series resonance also has the same frequency, 1 upon under root 2. I'm clicking here. I'm going back here. Right? Same frequencies. All right. All the definitions remain the same. So everything same here. And we have a few more. So we can find the inductor current and the capacitor current, and it could be much higher than the actual. So you can see that it is Q times the maximum current. Because of the open circuit and short circuit thing, we have higher capacitor and inductor currents. So again, the same way, luckily looks like the same expression, I think, except for the first term. And the bit is like this. Quality factor. Again, for high Q circuits, we can say that the omega naught is the center point of omega 1 and omega 2. So b upon 2 each sides. So this is a summary of all the series in parallel resonance. So luckily they are same. They are same but reciprocal. See, actually the whole of things is like reciprocal. Reciprocal. They are same. And I think this is also same, 1 upon 2q square omega naught plus minus. Yeah. So these are the values that at least right now I want you to remember. Later on, maybe we'll see if we can give it in the exam or not. All right, I want to finish it off with this particular question. Very similar. We need to find all those values. So omega naught is 1 upon under root LC, finding inputting the values there. Q again using the formula. For a high Q circuit, we can go about omega naught. So plus and minus b upon 2. So this is it. Don't mix it up. That omega 1 should be negative because omega 1 is smaller than omega 2 by definition. And what else? At omega naught, this is just R. Remember that the X and the L components are cancelled out. So V upon Z. V upon Z is like V upon R actually. Let's type it. We told you before. Power dissipation half I square R. Okay. Or Vm square upon 2R. We can get omega 1 and omega 2. This is 2 and this is half of, so 4R. Are you guys following? It's a bit too fast, but it's the same thing, just putting the values in the formula. Okay, this is, I believe, the last slide for today. I think so. Yes. I was hoping to finish off before 6, but not too successful. All right, any question? Tomorrow we'll be doing a tutorial, but I would again give you some opportunity to, if someone wants to ask question from the test point of view, they can ask tomorrow. Otherwise, we'll do questions for the chapter 3. Any question? I would again ask Jocelyn to please make the survey on the teams. If she has already made, please mark your feedback. Yeah, one more thing. I will be having a quiz tomorrow with you. After tomorrow, like after the tutorial, it will be about the basic concepts. So it's not solving. It will be like sort of multiple choice questions or true or false or things like that. So that quiz will be after tomorrow's tutorial. Probably maybe depending upon the time that you guys suggest. But it will be tomorrow so that I can catch you guys fresh with the fresh memories, sweet memories of this lecture. Guys, please provide your feedback on the chat window. Thank you, Jocelyn. Later, please pass it on to me. Any question? Any question, guys? Okay, then those who are done with the attendance and those who are done with the survey, they're allowed to leave the session. Thank you very much.
Thank you, sir.
You're welcome. Reminder once again, tomorrow tutorial and next Monday test. Off one. Don't forget to provide the feedback. You're welcome. Welcome everyone. Carlos, Tan, Henchin, Ong, Arif, Nabian, thank you. Web results. Anything? Thank you, Jocelyn. Guy, thank you. Welcome. Nazirul, thank you. You're welcome, Mohiman. Asfar, you're welcome. Same to you. All right, thank you. You guys can leave. Thank you very much. Please provide feedback once again and mark your attendance. Don't forget. Thank you, Atika. I will share the slides and the video once available. I'm stopping the recording.